Differential pair with MOS loads. The load of a differential pair need not be implemented by linear resistors, as with the common source stages studied in chapter. Differential pairs can employ diode connected to current source loads. Figure the small signal differential gain can be derived using figure differential pair with A diode connected and B current source loads. Half circuit concept for figure A, AV equal to minus GMN GMP power minus 1 parallel R naught 10 parallel R naught P, similar to minus GMN by GMP, where subscripts N and P denote NMOS and PMOS respectively, expressing GMN and GMP in terms of device dimensions. We have AV similar to minus root over nu N W by L and by nu P W by L P. For figure B, we have AV equal to minus GMN R naught N parallel to R naught P. In the circuit of figure A, the diode connected loads consume voltage headroom, thus creating a trade-off between the output voltage swings, the voltage gain, and the input CM range. Recall from equation that for given bias current and input device dimensions, the circuit's gain and the PMOS overdrive voltage scale together to achieve a higher gain. W by LP must decrease, thereby increasing mod VGSP minus VTHP and lowering the CM level at nodes X and Y. In order to alleviate the above difficulty, the part of the bias currents of the input transistors can be provided by PMOS current sources illustrated in figure. The idea is to lower the GM of the load devices by reducing their current rather than their aspect ratio. For example, figure addition of current sources to increase the voltage gain. If M5 and M6 carry 80% of the current of M1 and M2, the current through M3 and M4 is reduced by a factor of 5. For a given delta VGSP minus VTHP, this translates to a factor of 5 reduction in the transconductance of M3 and M4, because the aspect ratio of the devices can be lowered by the same factor. Thus, the differential gain is now approximately 5 times that of the case with no PMOS current sources. The small signal gain of the differential pair with current source loads is relatively low, in the range of 10 to 20 in micron technologies. How do we increase the voltage gain? Borrowing ideas from the amplifiers in chapter, we increase the output impedance of both PMOS and NMOS devices by cascading, in essence creating a differential version of the cascade stage introduced in chapter. The result is depicted in figure A. To calculate the gain, we construct the half circuit of figure B with which is similar to the cascade stage of figure. Thus, mod AV is similar to GM1 into GM3 R03 R01 parallel to GM5 R05 R07. Cascading therefore increases the differential gain substantially but at the low cost of consuming more voltage headroom. As a final note, we should mention that high gain fully differential amplifiers require a means of defining the output common mode level. For example, figure B, the output common mode level is not well defined, whereas in figure you can see in this figure A cascode differential pair, B half circuit of A diode connected transistors define the output CM level as VDD minus VGSP. We return to this issue in chapter. Thank you.